Hello, we are talking about today 3D lines. It's not that the line itself is three-dimensional, it's that the line is placed in a 3D space. And we want to talk about what happens there. So remember that the scalar notation does not work when you attempt to use it to describe a line in 3 dimensions, sometimes 3D, sometimes called 3 space. So instead, we'll use only the vector and parametric versions as described in the previous section. And anyway, that'll be our line, okay? So the vector notation is the only method working, okay? I know I've said this a bunch, so I think you guys have that figured out. It's basically the same formula, right? RO plus T times M, all right? And basically what's going on here is that we are trying to just define a point in 3 dimensions. And so this vector will point to it. And how do you find this vector? Well, you add the starting point, which the user, the author of the line needs to define, okay? And the slope of the line is here. So this is its rise, its run. Sorry, that's the rise, and that's the run, and that's Z. Oh, wait a minute. So this is actually the rise over here, if you think about it kind of now more in a 3-dimensional sense. So the rise, instead of being the Y component, is the Z component. And the run itself is actually a, left-right run and a forward-backward run. All right, so you would run, forward 3, left 2, and rise 1. And you would, if you do that, starting from this point, okay, you would effectively stay on the line. And you could do that as far as you'd like. That's what the T value does. Remember that T value. All right. So let's just sort of get to know this 3-dimensional thing, right? So remember I mentioned before, we're going to jump right into 3D, but in the end, it's not much different than 2D. You just end up having to deal with that extra Z component here, here, and here. So determine a vector and parametric equation of a line, and it goes through these 2 points here, all right? So this is like a question we've done before. So I know that the vector equation of a line looks like this. All right. It looks like that. And, well, what's in here? Some point on the line. And what's in here? Well, it's some slope of the line. All right. Well, we've got a point. One of our points is 1, 2, 3. By the way, you could put either E or D in here. So I'm going to write just point. And this is going to be our slope. Well, the slope formula, to get the x, the change in x, the change in y, and the change in z, I'm basically going to be taking z minus, z2 minus z1, y2 minus y1, and x2 minus x1, right? And so I'm going to do negative 6 minus 3, negative 5, minus 2, and negative 4 minus 1. And so I'm getting a negative 9, 6, 7, negative 7, and negative 5. Looks like our slope is negative 5, negative 7, negative 9, right? And that's going to be our slope, or our line, right? Now, if I want to write it in parametric form, remember, parametric form, you just define each of the points each of the coordinates, the x, the y, and the z coordinate individually. So my x coordinate is 1 minus 5t. My z coordinate is 2 minus 7t. And my z coordinate is 3 minus 9t. I think I called this one z, and it's actually y. So just, clear that up. There it is. Pretty simple. We hardly wrote much at all, and we were able to define a line that goes through 2 points, E and D. Now what we're going to do is we're going to define a line that's parallel to the line in example 6, and it goes through point F. Oh, well, I've got this line in example 6. I'll copy it down over here. XYZ. And it's got a 1, a 2, and a 3, and a -5, a -7, and a -9 for its slope. Now, in order to be parallel to this line, this is called line 1, I'm going to make a new line. I'll call it line 2, and it's got its own infinite set of coordinates here, and it's got its own point. Oh wait, well, it needs to go through point F. So, well, let's just make point F the starting point. And then over here, I need a slope. Well, if it's parallel to this line, well, I might as well just use the same slope. There you go. And here, I'm going to call this a parameter W. It's one thing you want to get used to is if you have multiple lines, you need to give them different parameters, okay? What, our textbook chooses other letters. I've seen other references that do things like T1 and T2, right, in a reference to the line name as well. So I don't know. It's up to you how you do that. Oh, now we need a line that's perpendicular to this previous one. All right. Well, again, what I'll do is, I won't even copy the line down because I think there's space here. So we've got line 3 that it's got its own infinite set of points, and it's got a starting point. It's got its own parameter, which I guess I'll call T3, like the movie. Anyway, there, a bit more space here. Now the question is, I need something that's perpendicular, right? Well, in order to create a vector that's perpendicular to this vector, I just need to, I'll give this vector a name. This vector's name is M2, right? I need to make sure I create a new vector that's called, M3, and it's got its own, or when I dot it, I get a 0, right? So I'm going to write M2 down, -5, -7, -9. I'm going to dot with it a new vector. Problem with this vector is it's got 3 variables. So what you do is when you just need to create some vector that's perpendicular to some other vector, you just invent 2 of its components. And the last one I usually just call Z. I set it equal to 0. And what happens is now Z automatically adjusts itself after if you perform algebra correctly, such that the resulting 2 vectors become perpendicular. So it's -5 plus a -7 plus, that was supposed to be a 7. -7 plus a -9z should equal 0, right? And so if I add 7 and 5 over to the other side, I'm going to be getting 12. So z is 12 over negative 9, which I guess we can write as 4/3. And so 1, negative 4/3 is our vector. And we got negative 5, negative 7, negative 9. No, that's not correct. I mean, I can write that in here, but I don't want to just write it casually like that. Question is what point goes in here, right? What point goes in here? It turns out all I've said in this example is that I just need a line that's perpendicular to the line in example 7. Example 7, is basically, I guess, this line that I made here. In order to be perpendicular to a line, do you have to intersect it? In a way, maybe, maybe not. And so basically what I'm going to use is I'm going to use this guy's point here. Okay? That way I know that they're at a right angle to each other and they also intersect. So therefore they're perpendicular, right? Now that just a quick thing is in order to be perpendicular, you don't have to intersect. It's not part of the definition. In 2 dimensions, you automatically intersect. 2 lines in 2D that are perpendicular. There's a line, and then here's the other line that's perpendicular to it. Oh, it'll automatically at some point intersect. But in 3D, imagine this line right here that I'm pointing at. Imagine raising this line up towards the viewer a few coordinates. You can still argue that they're perpendicular, but do they really intersect? Anyway, if that is the case, if you're starting to talk 3D, well, then they have a new word for it, which is called orthogonal. Okay, and so I think that's why there's the idea of orthogonal, is because you can sort of be perpendicular without intersecting in 3 dimensions, and so they kind of decide, oh, let's make a new word for it. All right. We want to determine the intercepts of the example in line 8. Okay. Well, line 8 is line 3, I guess. And so we're going to do a 7, a negative 8. Oops, I messed that up. Remember, it's an X, a Y, and a Z. An X, a Y, and a Z. Oh, I'll switch to blue for this example. It's pretty nice blue, actually. And this is T3. And we've got a 7, a negative 8, and a 9. We got a 1, and a 4/3. And what we're going to do is we're going to try and determine the intercepts for this line. Okay? So now, let's talk about intercepts really quickly. So the rule of thumb for defining an x-intercept, remember, this is in 2 dimensions. In 2 dimensions. And to find an x-intercept, you set y equal to 0 because all the points on the x-axis have a y-coordinate of 0, right? And then likewise, to find the y-intercept, all the points on the y-axis have an x-coordinate of 0. And so you use that idea and you say, for the y-intercept, you set x equal to 0. For the x-intercept, you set y equal to 0. Well, now we got this new z component, right? Yeah. And so let's draw z out here. Oh, well, actually, this is x. That's y. And this is z. If you remember, that's how we were doing it. So now imagine a line that's like maybe here, floating sort of above the z x-axis. And then there's another point over here that's floating above the y-axis. And imagine drawing a line that goes through both of those. Guess what? This line that I've just drawn here doesn't have an x-intercept. It doesn't have a y-intercept. And it actually won't have a z-intercept either. It's actually not intercepting anything. So when you're asked to find the intercepts for this stuff, you actually might not find any answers, okay? Well, anyway, how do you find it? Well, what you do is to find the x-intercept, you set y, find the x-intercept. You set y and z equal to 0. So I'm going to go x, 0, and 0. And I'm going to use the parametric form, right? Well, x equals 9 plus t3 times 1, right? And so, apparently, in this scenario, t3 is negative 9. All right? No, sorry, I messed that up. My mistake. No, I'm setting, yes, those guys equal to 0. Sorry about that. And so I need a negative 8 plus 1 t3. And then I need a 9 plus 4/3 t3. And I'm going to write these guys a little differently. I'm just going to write this guy as a simple t sub 3. And this is a 4 t sub 3 over 3. All right, now I'm going to focus in on this. Basically, if you look closely at this, these two guys can be immediately solved for t3. All right? Now, and in the end, if I get the same t3, in both of these scenarios, then there is an x-intercept, and I can find it by taking that t3 and plugging it in here. All right? So basically what you want to do is you want to solve for t3 here and here. All right? And this is what I was trying to do before. t3 is going to be 8 in this scenario. Over here, t3 is going to be, well, let's see what I need to do here. I subtract 9. I multiply by 3, so I'm getting a 27 negative over 4, right? So I'm getting a negative 27 over 4. And basically, these guys, no, I didn't want to do that. I just want to write that these are not equal. Okay. And why is that the case? Well, basically what you're saying here is, let's go back to our diagram, is in order for me to have a x-intercept, right? I'll put this maybe in green. In order for me to have an x-intercept, the y-coordinate, right? The y-coordinate and the z-coordinate must be 0 at the same time, okay? At the same time. And so therefore, I go ahead and I set them equal to 0 and I find out, well, when is the y-coordinate 0? And when is the x-coordinate 0? Well, the y-coordinate is 0 at 8, so implying, to have a y-coordinate of 0, I would be sort of hovering somewhere above. So that would be here, right? Above the x-axis. So in this diagram, for example, my y-coordinate is 0. Oh, shoot. My y-coordinate is 0 here, right? But then imagine this line going down further like this. And then maybe my z coordinate is 0, probably like here, right? Does that make sense? So, and that's kind of the idea there. By the way, my y coordinate is 0 here because it's basically at this point on the line, I've got no left-rightness. And then over here, I've got no up-downness. And if my left-rightness and my up-downness were both 0 at the same time, I would be on the x-axis. Anyway, so that's kind of the idea there. It's always difficult to draw those on the graph, but hopefully that makes a little bit of sense here, right? Now, since we didn't find an x-intercept, well, let's go ahead and try to find a y-intercept. So to find a y-intercept, I set my x equal to 0, and I leave my y, and my z goes into 0. Ah, I didn't write zeros there. Well, I'll write it like this. I'll just kind of write it there. And so, basically, I kind of go where I write 9 plus t3, and here I'm getting a 9 plus 4 t3 over 3. Now, this is pretty nice because once I've solved all of this stuff, I've solved it, right? And so basically what we're looking at is here t3 is -9. Here t3 is always the -27 over 4. And since these are not equal, then therefore I've got no intercepts. Okay. By the way, if you're just looking for all intercepts, seems like actually the most efficient way is just set them all equal to 0. Solve. So, you know what I mean? And you just say like, well, x is equal to 0 at 9, -9. Y is equal to 0 at 8, and z is equal to 0 at there. And if any one of those combinations of 2 happen to be equal, you would have the other one's intercept at that point. Okay. So, for example, if the x component was 8 and the y one was both 8, you would know that you would have a z intercept. Anyway, there you go. I won't finish out the z one there, but I think you guys got that. And so there you go. There's some questions on intersections of, or no, not intersections, just regular lines. Okay, regular lines.